Thanks for the organizers giving me a chance to speak here. Today we will talk about the cohomology of non-orientable toric origami manifold. This is joint work with unknown Eisenberger and Professor Masuda and Sanjian Park, last speaker. First, we will introduce the construction of toric origami manifolds. This was introduced by Canas da Silva and Gilman and Pierce. In fact, at the same time, there are different generalizations of projective toric manifolds. For example, Ishida and Fukukawa and Masuda give the definition of topological toric manifold, and these three mathematicians give the definition of toric origami manifolds, and also from algebra geometry point of view, Cafe, Govansky, and Lazarfeld and Mutstada have introduced the definition of Okonkov bodies. First, let's recall the definition of symplectic manifold. That is a manifold, smooth manifold with a closed Q form. Moreover, omega is non-degenerate. From these conditions, we can get that the dimension is even, and this manifold is always orientable. Moreover, if M is a compatible manifold, then the second cohomology never vanishes. Let's see some examples. For example, R2, we have the standard form dyi. This is a standard symplectic manifold. Another one is any closed Riemann surfaces, and the form is given by the area form. We can also see some counterexamples. For example, RP2N. This is not a symplectic because this is non-orientable. But later we will show that this is toric origami manifold. Another one is S2n. If n is large or equal to 2, this is not symplectic, but this is also a toric origami manifold. Now we will introduce a folded symplectic manifold that is also M is smooth. This is a Q form. If we allow that this top form is vanishes transverse at some subset. Here the transverse means omega n can be viewed as a section from M to this line bundle. Then the graph, if this is M, then the graph is something like this. This is transverse means. And moreover require that because this condition is always a submanifold codimension 1. This is called folding hypersurfaces. We require that the pullback has maximal rank, that is L star omega n minus 1 does not vanishes. We can also see some examples.
Is Z a manifold?
Yeah, this because of this transverse condition. Yeah.
It possibly is this kind, right?
Yeah. This is very important. Yeah. This is a folded symplectic form on R2M, and the fold is x1 equal to 0. Another one is S2n. We can give it a folded symplectic structure. We can view it as a subspace in Cn direct sum R, and this coordinate is Z1 to Zn, and this is the head function. Then omega is given by then this is a form in the larger space, then restriction it on S2n. This is a folded symplectic form. And
omega is 2 over something of what is it? What is the first coefficient? What is that?
this is minus 1 root square.
Okay.
Sorry. And the folding hypersurface is equator after calculation. Now we can come to the definition of origami manifolds. First, we require this is a folded symplectic manifold. So we have a Z, the folding hypersurface. Then for any P belong to Z, we have a map. This gives you a one-dimension corner. This can be seen from the local chart. So this is called the non-foliation on Z. So now we require Z has a principal circle bundle structure. And this B we require this is compact. Moreover, we require that because this has a circle bundle structure, so that we can decomposition of the tangent space along the fiber direction and the horizontal direction. So this along the fiber direction is just given by the corner. So this is the idea of the origami manifolds. So now we can give the definition of toric origami manifold. Of course, we require this is first is origami manifolds. Also, we require there is action. This action is effective. Moreover, it preserves the forms. Like the symplectic case, we will also require momentum map. This is mu from M to the due of the Lie algebra. Momentum map means this map is equivalent because this is abelian, so this action is trivial. Moreover, we require that have this equation for any Let's see an example. The typical example is S4 with the form we introduce first. Then the torus action is given by in this way. And the momentum map by this form. For torical origami manifold, we can also talk about the orientable or non-orientable. But moreover, we will introduce another concept is called co-orientable. just now we have a vanishing subset Z. Usually this is not connected, so it has many components. We say M is co-orientable if each component of Z has a orientable neighborhood. For example, the picture is something like this. This is Z. And in this part, because this neighborhood is orientable, then we can talk about the positive or negative locally.
What is the definition of co-orientable?
That is.
You can give an orientation on Z, such that, or what?
Yeah, the neighborhood of Z is orientable.
Neighborhood of G is orientable.
Yeah.
Number form is
Yeah. In fact, if
Is it possible that there's a Z cannot be co-orientable?
Z co-orientable.
Z is always co-orientable, that's what you're saying?
No. We just give the definition of co-orientable. There is an example of Z is not co-orientable. The typical example is.
Oh, yeah. Okay.
Yeah.
But if you start out with orientable 2n manifold M,
Yeah, in this talk we will talk about co-orientable case.
so if you have if you start out with the origami manifold,
Yeah.
which is orientable, then this Z has to be orientable.
Yeah.
Yeah, so it should be orientable. It's a co-orientable.
Yeah, Z is always orientable.
Z is always orientable.
Yeah, because we have this requirement. This is a principal bundle and this is compact. In fact, this is a symplectic manifold because of this have a maximum rank. So it can reduce a symplectic form on B. So Z is always orientable. For example, in this one, Z is this.
But originally, if M is already orientable, then you always have a co-orientable.
Yeah, but the converse is not true.
But if you start out with the non-orientable manifold, but still you can have a co-orientable subset Z.
Yeah. For example, now we have a Toric origami manifold. If we have 3 pieces, this must have different signs. So this has no choice. This is no orientable, but this is co-orientable. Now, you can talk about the classification theorem of Toric origami manifolds. This was Canis da Silva and Gilman and Pierce result. They generalize the horizontal theorem. Their result is 2-dimensional Toric origami manifold is 1-to-1 corresponding to n-dimensional origami templates. Later we will introduce this part. This is a combinatorial object, and this is a geometry object. And this corresponding is given by the moment map. If there is M, the template is determined by the image. Roughly speaking, the origami template is just a collection of horizontal polytopes. We group them with some compatibility conditions. A horizontal polytope first is a n-dimension polytope, and also require this is simple. Simple means at each vertex there is just n edges, and also require this is rational. At the vertex W, the edge have this form. We require U is belong to Zn if you take the standard basis on Rn. And it is called a non-singular if U1, that the Un forms a Z basis of Zn. Now we want to describe the origami templates by graphs, because later we will we want to use the lifting of the graph to research the lifting of the non-orientable Toric origami manifolds. First, that G is a connected graph, and the loops and the multi-edges is allowed, and the V is denoted the set of vertex, and the E is denoted the set of edges, and we use the Dn to denote the set of all the horizontal polytopes in Rn. And Fn is all the facets of the horizontal polytopes. So origami template, in fact, is consistent of the three members. First, we have a connected graph, and have a map, xi V and xi E. Xi V is from V to the horizontal polytopes. And the xi E is from E to Fn, to the facet. But we require some conditions. If V1 and V2 are two vertices and has an edge E, we require that this facet is a facet of V1 and V2. They are common facet. Moreover, we require that the neighborhood of this facet is the same. This neighborhood is the same. And the third condition is that from vertex V, we have two edges, E1 and E2. Then we require that these two facets, the intersection of these two facets is empty. In fact, this is come to the fact that if we have a Toric origami manifold, then we have many pieces of Z. This Z, in fact, is corresponding to the facet after the moment map. We call the origami template is co-orientable if there is no loops in the graph. And we say it orientable if this graph is two-colorable. Two-colorable means if there is a function from vertex set to 0, 1 and if two vertex connected by an edge, then their values are different. So in fact, canvas does silver and the course's result in fact imply that the co-orientable Toric origami manifold is one-to-one corresponding to the co-orientable origami templates. There is one remark is that we know this moment map is equivalent, so this induces a map from the orbit space to this one. For the toric case, we know that these two things are homomorphism as manifold with corners, but for toric origami case, usually this is not true. However, this is always isomorphism to the resulting space of the origami template. The resulting space means, for example, we know that this orbital space looks like this one, a manifold with corners, but the corresponding origami templates is this one. They are homomorphism.
Like you have a Toric origami manifold.
Yeah.
You have vertices. I mean, you have fixed points.
Yeah.
The action. The fixed point seems to correspond to the vertices of this Toric origami template.
Yeah, yeah.
And then what about this delta and polito, which you are sort of holding for each vertex? You have delta and polito corresponding. PV maps each vertex to delta and polito, right?
Yeah.
So how do you get delta and polito from the origami manifold? I mean, you said you have a M quotient P is isomorphic to to this underlying space of
Yeah, yeah,
origami template. So
Yeah.
for each vertex you associate, by PV you associate delta politer, right?
yeah.
So which delta politer is, how this delta politer is associated? Or it will be coming out in
In fact, is from this part
yeah.
we can get the symplectic toric manifold. Is that okay? Just like connect Z, each Z, then we get many symplectic toric manifold. Then by the momentum map, we can get the a connection of disjunct polytopes. And conversely, is that okay?
Okay, go ahead. Go ahead. And I will talk to you later privately.
Okay. So now, how about the cohomology? Because their classification theorem, we want to describe the cohomology in terms of the orbital space in a combinatorial way. In fact, Toric and Pierce have shown that if this template is co-orientable and each face of M over T is acyclic, then the order degree vanishes.
What does it mean base?
Because this, we know that this is a growing of disjunct polytopes. From this part, we can talk about the phase structure.
There is something like a folded base that is also kind of base.
Yeah, this is a phase.
I mean the folded part.
Yeah. No, that is not a phase. Yeah. In fact, this you can add the resulting space. Yeah.
And that folded face is itself is face or it doesn't matter. I mean, what does it mean face here? So that is.
So this is a vertex.
Yes.
So this is one face. This is another vertex. And
All space is a light with gold.
Okay.
yeah, yeah.
What is, I mean, do you remind me what was the co-orientability of this origami template? What do you mean by
Yeah.
origami template is co-oriented?
In here, this is corresponding to S3. So the neighborhood of S3 in S4 is orientable. So this is, of course, co-orientable. Co-orientable is just a local property. Yeah.
But this is a purely combinatorial object, isn't it? There's this origami template.
Yeah.
So by just from combinatorial object, you said this is co-orientable. What does that mean? Does it? You have to go to the manifold.
If we for this disjunct polytope denoted by a vertex, another by another vertex, if they have a common facet, they will connect them. So this graph has no loops, so this is co-orientable.
So loop that does not have any loop, then it's called.
Yeah. There is a classification theorem. we have generalized the result is that if M is rentable and each proper phase of M over T is acyclic, but M over T can be arbitrary. Then we show that the B1 is equal to B2 minus 1 is equal to the first beta number of the orbital space. Moreover, other order degree vanishes. And for the even degree part, we can describe the even degree part by the H vectors. That is B0 equal to H0. We have this, moreover. Now, in fact, in this argument in the proof, we just use the Merva-Torres sequence and the Pongari duality.
So, how much is the hypothesis and how much is the result? I don't know. Your statement looks very confusing. So, which is the hypothesis of this? M is orientable. That's the only hypothesis, or
yeah,
is result?
Yeah. This is assumed. This part.
That's the hypothesis. So
yeah.
each proper phase of M. Each proper phase of MT is what?
It's sorry, I forgot to write it.
Then
Here, the results, the manifold is a torus manifold, right?
Yeah,
Origami.
it's always a torus manifold.
Here, M just origami.
Oh, origami. Toric origami, sorry. Always toric origami. Moreover, this is torsion free. We can calculate that. In fact, we can generalize this result to co-orientable case. Yeah.
Here, the obvious space is just a manifold with a corner.
Yeah.
Which has also its own Beatty numbers, right? Not only Toric origami manifold has its own Beatty numbers, right?
Yeah.
Here, you write B1 and there is B5, B2N. That's the manifold of the Beatty number of manifold.
Manifold. Sorry.
There are all these.
Yeah.
so every vector number can be expressed as a H number and first vector number of the order space.
Yeah. Yeah. Now, if M is co-orientable, also each proper phase of M over T is acyclic, then almost
If M is co-orientable or Z is co-orientable?
M is co-orientable means each component of Z has a
So M is not necessarily orientable, but it's local.
Yeah.
By the way, why do you put umlaut on O? Oriental. Why do you put two dots? Is it German or?
Because in the Orangian reference, they use this one. So
That's German, is it? To umlaut. So you put double dots. Why do you? Who was the German behind?
yeah, this is the same under 2i also equal to hi minus b1 m over t, but this is, and also b3 equal to 0. b1m also equal to bm over t, but the change is b2m minus 1m equal to b1 m over t minus 1. This part is changed, and another one is z2. If m is not, co-orientable but non-orientable.
Maybe you can determine the homotopy type of orbit space.
The orbit? Homotopy?
Homotopy.
Yeah, that is just is the same of the graph.
Some the
Homotopy type
of the
circles. Yeah. So that is just have this.
The higher dimensional Betti number, the values.
Yeah, of the orbit space.
It's only one.
Yeah. Now we will talk about the idea of the proof is quite simple. First we have G. We have this one. This is non-orientable. That is to say, this is not two-colorable. We can give a lifting that it become two-colorable. We can give an example to say the idea. This graph is not two-color, but we can construct another one, 1, 1 prime, 2 and 2 prime. That is 1 connect to 2 prime, and 2 prime goes to 3, and 3 goes to 1 prime. 1 prime goes to 2, like this. This graph is two-colorable. From these two graphs, we can also construct this one and this one. So we can also construct the origami template, and by their classification theorem, so we can construct a double covering of M. This is orientable, and each proper phase is also acyclic. Then can use our previous result. One more, we need to say that we have used Brush's result. Brush's result says that if we can use X, if X is a non-orientable manifold and X hat is double covering this n-dimension manifold, then we have Bn x hat is always equal to Bix plus Bn minus I x. So from this result we can see that because this B3 and B5 and B2 minus 3 vanished, so this also have vanishes. And for the Z2 coefficient, we can also this is non-orientable. For Z2 coefficient, we can use the Poincare duality. And in fact, we can also show that except the two torsions, there is no other torsions by the transfer homomorphisms. Yeah, that's all. Thank you very much.